This is problem 544 in the back of your chapter. Here we have a nuclear power plant that generates 750 megawatts. We're told that the reactor temperature is 315 degrees C, and we have a river temperature, water temperature of 20 degrees C. First thing we're asked to find, what is the maximum possible thermal efficiency of this power plant, and what is the minimum rate at which heat must be discarded to the river? So let's attack that part of the problem first. So the first thing we need to realize is what kind of basic problem is this? And the answer to that is this is a second law problem because we're interested in thermal efficiency. This is a heat engine, basically a heat engine. We're interested in the thermal efficiency of this heat engine, and we want to know what? We want to know, we were given the temperatures, we want to know what is the minimum amount of heat that must be discarded to the river. So if we think back to what we had earlier in the chapter, this, any kind of heat engine can be modeled like this, where we have a hot temperature reservoir, thermal reservoir. This engine brings in heat, it produces work, and then it has to reject some of that heat to the cold thermal reservoir. Now, if you look back in chapter 5, it discusses that these power plants and the heat engines can basically be modeled like this. One of the things that we'll talk about is that this power cycle, so the steam power generation cycle is a closed system. And your book mentions that briefly, I believe, in your, on page 175, your book mentions that briefly. It's not something that the book emphasizes, but I wanted to do this problem so that you realize this. We'll be covering this power generation cycle in a little bit more detail, I believe, in chapters 7, 8, and 9. But this is a closed system, and let's write down what we want to find. What do we want to find out of this? We want to find the maximum thermal efficiency, and we want to find the minimum rate at which heat must be discarded to the river. So this is going to be a QC. So the first thing I would do is think about, let's look at some of the definitions here. The thermal efficiency of a heat engine is equal to minus W divided by QH. All right, that's the definition of the thermal efficiency. That is, how much work do we get out of an engine when we put a certain amount of heat. And the reason we have the minus sign is because work that's leaving our system is negative, so that we have a positive efficiency. So that's the first thing I would want to think about when I'm solving this problem, is the maximum thermal efficiency. Now, as I said, this is the thermal efficiency. What is the maximum efficiency for any kind of heat engine? The maximum thermal efficiency, the maximum efficiency for any kind of heat engine is what we get from the Carnot engine. So what we're going to do is we're going to insert, instead of the turbines that you would find in a nuclear power plant. So we've got the nuclear fuel that is producing heat, which is converting liquid water to steam. The steam then hits the turbine blades, generates the work. Some of that, then that steam is condensed. Some of that heat is rejected to the environment, and that steam is recycled then to be heated, and we have this cycle, this closed system. We're going to replace all the turbines and machinery there with this theoretical Carnot engine. So, I mean, it really doesn't may not make a whole lot of practical sense, but that's the usefulness of this Carnot engine. It gives us a maximum efficiency for any kind of heat engine operating between two different thermal reservoirs. So what we do then is we go to our textbook and we look up the thermal efficiency of a Carnot engine. This is equation 5.7, and this is equal to 1 minus, there's a couple different forms, but this is the most convenient form, 1 minus Tc divided by Th. So the temperature of our thermal reservoirs. And so that's 1 minus temperature of our cold reservoir is 20 degrees C. But what you have to remember is that, especially when we're doing second law problems, always use Kelvin. We always use absolute temperature. So this is 298.15 Kelvin. And then our hot reservoir, this is the reactor. This will be what? 588.15 Kelvin. All right. So our Carnot, or our maximum thermal efficiency, is going to be 0.5016, or about 50%. So what that is saying is that if we had a reactor that is generating heat at this temperature, and we were expelling heat to a river flowing by at this temperature, the maximum amount of work we could get out of here would be about 50% of the heat that's being put into it. All right? There's no way we can go any higher than that. Okay, so that's the first part of part A. The second part of part A says, what is the minimum rate at which heat must be discarded to the river? And so what are we asking for here? We're asking for QC. And we want the minimum amount. Well, let's think about that. What's the minimum amount of heat that would be discarded? Well, that would be for a Carnot engine, all right? Because remember, a Carnot engine is going to extract the maximum amount of work out of the heat that's available. So that means the minimum amount of heat will be discarded to the surroundings. So there's a couple different ways you can approach this problem. There are a whole bunch of equations on pages 176 and 177. We want to find QC minimum, so this is QC for a Carnot engine. So you've got a couple different ways to solve this. The easiest way I would solve this is to realize that this Carnot engine is a closed system. Right? We already know the efficiency. The efficiency of a Carnot engine, of this Carnot engine, is 0.5016. All right. The amount of work, and this is also equal to, so we can write this for, we have this for a Carnot engine. We can also write this for a Carnot engine. So this is equal to minus the work for a Carnot engine divided by QH for a Carnot engine. All right. What's the work for this Carnot engine? Well, the work, we're pretending that this is a Carnot engine that's generating 750 megawatts, right? And so what we can do then is we can calculate QH for the Carnot engine. If we know that, and we know that we have a closed system, we know that for the overall process, delta U is equal to Q plus W. For a closed process, for a closed system, delta U is 0, because we're going right back to where we started from in our little cyclic process, whether or not this is the actual steam generation process or this theoretical Carnot engine that's in here. And so we get Q is equal to minus W. Q is equal to what? Q is equal to QC plus QH, and that's equal to minus W. All right. So this is all for Carnot engines. Remember, we're sticking with Carnot engines for this process. So what I can do then is I can plug in my 750 megawatts, I can calculate QH, and then from there I can calculate QC. So if I do that, QH for the Carnot engine is equal to what? It's 1.495 times 10 to the 9th watts. It's a lot of watts. All right. So what I did was I plugged in minus 750 megawatts, so that's 10 to the 6 watts. I get 1.495 times 10 to the 9th watts for QH. And then I have QC is equal to minus W minus QH. So all I've done is move QH over there. And so this is what? This is minus 750 megawatts. And I'll put that as 10 to the 6 watts. Because remember, work that's being produced is negative. So I have minus a minus. And then minus QH. QH is 1.495 times 10 to the 9 watts. QC, we do the math, is minus 7.45 times 10 to the 8th watts. So this is our, and in this case, because we're dealing with a Carnot engine, remember everything for this part of the problem, we're assuming it's a Carnot engine. Part A, everything is a Carnot engine. So this is going to be the minimum amount of heat that would be expelled to the thermal reservoir for this. And we have a negative sign. Does that make sense? Yes, it does, because heat being expelled from our system will be negative. All right. So now let's look at the second part of the problem. It says if the actual thermal efficiency of the plant is 60% of the maximum, at what rate must heat be discarded to the river? So the real thermal efficiency is going to be equal to 60% of the maximum efficiency, which is the Carnot efficiency. And so let's do that calculation first. So the real thermal efficiency is going to be 0.6 times 0.5, which is about 0.3. So about 30%. So that is the real efficiency. At what rate must heat be discarded to the river? So now what we want to do is we want to find QC for the real process. So how do we approach that? Well, it's the same kind of calculation that we did before. It's just that now we're dealing with the real process. So the way I would approach it is, I think the easiest way, or one of the easier ways to approach it, is to go back to our definition. We've calculated that the real thermal efficiency is equal to 0.3, and what is that equal to? That's equal to minus the work divided by QH. And this is, I'm going to write the real work and the real QH that's coming into the system. All right? The real work is 750 megawatts. And so we're left with one equation, one unknown. We can calculate QH for the real process, and that is equal to 2.492 times 10 to the 9 watts. Is that bigger than what we had before? Yeah, we had about 1.495 times 10 to the 9th watts for the theoretical Carnot heat engine. So that makes sense. Our actual heat that has to come in to generate this. So one of the confusing things might be, well, how come I use 750 megawatts for the Carnot engine? I was using that because we were assuming that everything was as efficient as possible. We were wanting to find this QH and QC. For that efficient Carnot engine, we have the minimum amount of heat being absorbed and expelled to produce this amount of work. All right. There's several ways you can think of it. We're getting the maximum amount of work from QH, expelling the minimum amount of QC, right? Or we're using the minimum amount of QH to generate the amount of work that this heat engine, that this thermal cycle is producing. So if it's confusing, just think about it for about 30 minutes. Hopefully it'll eventually percolate and make sense. This is not something that I would expect you guys to just immediately take to. These are problems that you kind of have to sit and look about and think about for a while. So, but anyway, the point is that the amount of heat that comes into this real cycle is a lot more than what we had for the Carnot engine. All right. And so again, just to be complete, this is a closed system. And so this delta U is equal to Q plus W. Since it's a closed system, that's equal to 0. And so we're left with 0 is equal to QC plus QH plus W. We want to solve, we know what W is, we know what QH is, we want to solve for QC. QC is equal to minus QH minus W. We plug those values in, QH, we plug for QC, or sorry, for W, and we get minus 1.742 times 10 to the 9 watts. And our answer for the Carnot engine was a lot less. So that makes sense. So this is the amount of heat expelled to the river. And the rest of the problem asks you, what is the temperature rise of the river if it has a flow rate of 163 meters cubed per second? This would be an environmental engineering type of problem. All right, if we're what is one of the main concerns? Why are we concerned about the water temperature rising? Well, one concern might be dissolved oxygen levels, because generally, and in the case of oxygen, the dissolved oxygen level goes down. Oxygen is less soluble in warmer water, and so aquatic life will have less oxygen available. So this is essentially a energy balance problem where we have we know how much that, remember, this watts is joules per second, so we know how much heat goes into this is QC. We have this, you can take a 1 second basis. So in 1 second, we have 1.742 times 10 to the 9 joules of heat going in to our river. How much water is in here? This is 165 cubic meters in 1 second. All right, and so we can then look up the density, we can get the mass, and we can look up the specific heat, and then we can calculate delta T from the mass times specific heat delta T. So Q is equal to M C sub P delta T, and you can do that equation, solve for T2. All right.